like a fundamental type of stresses, shear and normal. So different behavior that you apply to the structure can create one of this type of stresses. For example, torsion creates shear stress. Bending creates normal stress. All right? So let's just learn these behaviors here. Torsional stress are basically when there is a torque applied to the system, you always can show it with the double-headed arrow. That's very common to show the torque with double-headed arrow. So what you use your right hand rule, right? So the direction of rotation really comes with when you put your thumbs towards the direction of the arrow, and rotation would be the rotation of your fingers, your palm, all right? So the direction, you can use the right hand rule to understand the direction of rotation. So something we want to understand is that in one cross section, all right? So the shear stress as a result of torsion or torque would be maximum, right, on the perimeter. So if I draw this one maybe in black, all right? All right. So it is maximum on the perimeter, and it gets lower and lower, reaching to 0 on the center of the area, center of the cross section. Okay, that's how the torsion behaves. So it is just going from radius, and on the maximum radius, which is on the perimeter, you have the maximum maximum torsional stress applied. So this is the formula for you. All right. Tau max is the shear stress, or tau. T is the torque, internal torque. Right? J is a torsional constant. Torsional constant. All right? So J for the circles, just something probably you want to know already for the circles, because the torsion is most common for the circles. So if the radius is C, the torsional constant of the circles would be pi C4/2. Okay. Bending stress would be this formula for it. Bending stress is a result of applying the bending moment, internal bending moment in the system. All right. The formula is my/I. So the bending moment in one section would be something like this. If I look at like this cross section, something like this, right? And this is your neutral axis per se, right? It is maximum on one end. It goes less and less reaching to the neutral axis, and then it goes to the other direction with the other side. For example, you would say it is compression on top, tension at the bottom, and it is a maximum on the farthest fiber away from the neutral axis. We usually say this is a Y, goes from the neutral axis. The maximum Y would be really the height of the member from the neutral axis, right? Over there, you are dealing with the maximum bending stress. All right. It can be dealt with the compression, one side, and the other side would be the opposite, tension. They can be switched. You can have compression at the bottom, tension on top. All right. This is what you're dealing with. Look at this. If this is a bending moment applied to my cross section, all right, it caused the bottom to be under tension now in this configuration, and the top to be under compression. Because if you think about it, this moment, what it's doing, it is pulling the bottom, pushing the top. Tension bottom, compression top. All right. This is another way of showing that. So in this case, if you think about it, on top region, we are dealing with the compression because of this behavior. On the bottom level, you're dealing with the tension because of this bending behavior applied to the system. Okay. And the formula, I introduced it to you here. So one thing before leaving this is that this Y starts from the neutral axis. Do not forget that. All right. So you're going to find the answer from this formula. If the sigma become more than 0, that side would be under tension. If sigma is less than 0, that side would be under compression. All right. So this M has a positive, negative. This Y also. This I is constant, always positive. Always positive. Okay. Let's continue. All right, it says the assembly consists of two 10mm diameter copper rods, AB and CD, and a 50mm diameter steel rod, EF, and the rigid bar G. All right, the bar G is rigid, so it means that it wouldn't deform. If the P is 5 kilonewton, all right, determine the normal stress in bar EF. So bar EF here. So it wants us to find the normal stress. All right. So if you want to solve these problems, finding the stress, always don't forget a stress. For a stress, we need internal forces. All right. So internal forces, how it can be found? By cutting the member. So we need to cut the member and look at inside, look at inside and derive and find the internal force using equilibrium equation, right? So if the member EF is requested from me, I know that I need to cut it. I need to cut and look at inside the member. All right. So if I cut it, I'm going to end up with the left and right side, just similar to problems we have solved so far. If that's the case, you know that, well, if I select the right side, it makes much more sense because, well, there is only one force, so you can easily find it. But the left side, you need to find the support reactions first, and then go from all the forces applied. All right. So I'm gonna cut member EF. All right. Somewhere at the middle. So it is F, and E would be somewhere here that we do not see at this point. So we have the force of 4P applied here, but we do not know what is the force here. I'm going to call it N. Okay. So summation of force in X direction equal to 0. This direction positive. We have negative N plus 4P equal to 0. So N is 4P. All right. So now we can say sigma, the stress, is equal to N over A. We know that axial force over the cross section. So the N is 4P, right, over the cross-sectional area. The cross-sectional area says the assembly consists of two 10mm copper for AB and CD, and 15 millimeters for EF. So I would say it is 15mm diameter, right? So we can say pi 0.015 meter as a diameter squared over 4. Okay, just change it into meters. For P, it told you that the force P is equal to 5 kilonewton. All right. So just for the sake of calculation, let's just make this in Newton as well. So we want to say 5,000 Newton. All right. So it would be what? It would be 4 times 5,000 over 3.14 over 0.015 squared times 4. All right, over 10 to the power of 6. So it is 113 0.2 megapascal. All right, this is a stress of member EF. Okay, so it was a large number. I divided over 10 to the power of 6 to get the megapascal, by the way. It was a large number divided over 10 to the power of 6 to get you in terms of megapascal, because the number was in Pascal, Newton over square meters. Let me just double check the digits. 4 times 5,000 times 4 over 3.14 over 0.015 squared. All right. All right, so this was the first question. The second says, how much is the bar EF will elongate? All right, the elongation. So you know that the elongation, axial elongation, can be found by the NL over EA. Remember that? So if this is a formula to follow for axial elongation, the N you have found 4P. So 4P is the force. The length of the member is 450 millimeters. So let's just say 450 10 to the power of negative 3 to make it in meters over E. So the E needs to be read from the manual. That's the point that you want to be comfortable to find the values from the manual. So the member is steel rod, right? So for the steel rod, if I go to, let's see if we can just do it comfortably here. It would be a little bit difficult since we are dealing with this. But we need to go to the handbook. God, what page would it be? So it is page. All right, so we are looking for E values for different materials, right? So modulus of elasticity here. For a steel, it would be 29,000 KSI, right? Can you see that here? Let me a little bit, I don't know, maybe zoom in. All right, here, for a steel A36, 29 KSI. 29 to the power 10 to the power of 3 KSI for E. All right. Page 139 from the handbook. So 29,000 KSI. Let's go back there. All right. So we have 29,000. Oh, sorry. We had to read the number in metric units. Let's see. So this is in KSI. Oh, it hasn't given us that the units would be, I think it is 200 megapascal. All right. I wish it would have been given us that. That would be much better, really. So the page before, given some numbers for a steel, yeah, here it says also. So in this page, it give you in the American, in the SI units as well. It says 200 gigapascal, right? 200 gigapascal for a steel modulus of elasticity. So 200 gigapascal. All right. So you would be saying 200 10 to the power of 9 Newton over square meters. All right. Multiply by the area you already have found. It would be pi over 4, 0.015 to the power of 2. All right. This P we have calculated to be already, now it is given to us, right? The P is given to be 5,000 Newton. All right. So the answer to this would be equal to, so 4 times 5,000 times 450, 10 to the power of negative 3 over 200 over 10 to the power of 9 over 3.14 times 0.015 squared over 4. Okay, so the answer I have found would be 0.00025 meters. 10 to the power of 3 would be 0.25 millimeters. All right. Questions? So if the problem was asking you what is the internal forces A, B, and CD, the same idea. You need to cut, use equilibrium, left and select the left and right, use equilibrium, find the internal force, and just continue the problem. The essence would be the same. Okay. So let's continue. All right, it says determine the maximum tensile and compressive bending stress in being if subjected to this moment equal to 4 kilopascal, sorry, 4 kips foot, kip foot. Maximum tensile and compressive stress. All right. So what is the maximum tension, maximum compression of bending stress? All right, we get this. So what is this formula for stress? The formula for bending stress would be negative my over I, right? So you need 3 elements. You need moment, you need the distance from the neutral axis, you need the moment of inertia. Moment given here, 4 kip foot, and giving you positive, no problem. So the distance from the neutral axis is needed and the moment of inertia of the section, all right? So for the very top and very bottom, you need to find, because at one side, you're gonna have the maximum tension, at the other side, at the very bottom, for example, you're gonna have maximum compression. So you need to find in these 2 pieces, very top, very bottom. The first problem you're dealing with is to find the neutral axis, because you do not know what is the neutral axis at this case, right? So we need to find the centroid and pass the neutral axis from the centroid, all right? So let's find the centroid. Would be y bar is equal to summation of y till the I, AI over summation of AIs, all right? So if I put my datum here for now and find the y from here, so it would be what? So the way that I can deal with this problem, I can say, just the way that it is shown, I'm gonna say 1 vertical member, 1 horizontal member, and 2 vertical members. So let's just write it down. So I'm starting with this vertical guy. So its centroid would be here, the centroid of this guy here, centroid of this guy here, and centroid of this guy here, right? Okay, starting with this guy. So for this one, the y tilde would be 5, right? 5 multiply its area. Area is what? 10 times half. Okay. Then let's look at this top one. This top one, the total length, if you think about it, it is 3 plus half plus half. Or let's just find the centroid first. The location of centroid is here, right? So does that make sense for you if I say its centroid length, like this guy, would be this? So how much is that? It would be 10 plus half a half, right? Okay. Which would be what? Would be 10.25, right? So I can say plus 10.25. Then the area, what is the area of that? Would be 3 plus half and half would be 4 times the height would be half. Okay. Then these two guys are like this. So first of all, there are 2 of them. So I'm going to say plus 2 because they are exactly the same. So then I'm going to say this height up to here. So this height is how much? Does that make sense for if I say it would be 1.5? Let's see, we can say that height would be, the total thing is what? 10. So 10 is up to this point, right? 10 is up to this point. So does that make sense for if I say it is 10 minus 3 over 2, right? So this guy would be 3 over 2, right? So 10 minus 3 over 2, which is, I don't know, like it would be 8.5, right? So we can say 2 times 8.5 times, so the areas of them would be 3.5, right? 3 times half. Oh, it is difficult to write there. All right. Over the summation of areas, what are the summation of areas? It would be 10 times half. For the bottom one would be basically 5 plus, for that top one would be what? Would be 3 plus half and half would be 4 times half would be 2 plus, and you have two of these areas. You have 3 times half, which would be 1.5. All right. So from this, your y bar would be equal to, so 5 times 10 times half plus 10.25 times 4 times half plus 2 times 8.5 times 3 times half over 5 plus 2 plus 3. It is 7.1 inches. All right, this is the centroid. So let's just draw the centroid one more time. So that is what we are dealing with. All right, so from this level, so your centroid would be location like this. So this would be 7.1, right? This height is half, right? This height is 3, okay? This is the neutral axis. All right? This would be what? Just for the sake of knowing that, would be the total height, which is 10 plus half. So 10.5 minus 7.1. That would be 3.4. All right? This is the dimensions. So we know the dimensions. Now you know that your y maximum on top would be what? Your max, y max on top would be 3.4. Your y max at the bottom is 7.1. Okay, so these are the two things we know that. So the only thing left, so you know this one too at this moment, you know the y. Let's find the moment of inertia. We need to also define the moment of inertia for this, but it's a very lengthy problem, by the way. You're not going to be given something like this, but you're solving this for you, so you know that all different things to solving this problem, really. You know, this is really lengthy problem. It's more of like a final exam problem of the mechanics of material. All right. So if you want to find the moment of inertia of this one again, now about the neutral axis, you need to find, don't forget that. About the neutral axis. All right, so let's just do that. So moment of inertia of the system would be equal to, all right, so I'm gonna use this middle one first. So the local moment of inertia of this one would be what? Would be, I'm finding about the x-axis, or the horizontal axis, right? So first I'm gonna say this length, which is half, times the height of it, which is 10 to the power of 3 over 12, plus the area 10 times half times the distance of the centroid to the neutral axis, right? This distance. Local centroid to the neutral axis would be what? Would be 7.1 minus 7.1 minus 5, right? If you say 7.1 minus 5, it's going to be that. All right. Plus the top one, this guy. It would be the length of this member is 3 plus half and half would be 4. The height half to the power of 3 over 12 plus the area 4 times half times the distance between the centroid to the neutral axis. It is talking about this distance. All right. So what is that distance? Does that make sense for if I say 3.4 minus half a half? All right. Third one is these two guys, right? Again, I'm gonna say plus 2. The moment of inertia of each of them would be, so it is 3 by half, right? So we can say it is half times 3 to the power of 3 over 12 plus the area would be half times 3. All right, now we are dealing with this, the centroid of this guy is here to the neutral axis. So we are talking about this distance. All right, so how we can find that? If you want to find that, so it is, does that make sense for you if I say this 3.4, right, minus the half, minus 3 over 2? One more time, 3.4 minus half, minus 3 over 2. So it would be 3.4 minus half, minus 3 over 2. All right. So the summation of all of this, let's just see, half times 10 to the power of 3 over 12. All right, plus 10 times half times 7.1 minus 5 squared. All right, plus 4 times half to the power of 3 over 12 plus 4 times half times 3.4 minus 0.25 squared plus 2 times half times 3 to the power of 3 would be 27 over 12 plus 2, 85.85 plus 2 times half times 3 times 3.4 minus half minus 1.5 squared. I got 91.73. All right. So we have found the moment of inertia as well. So you're just gonna plug into this formula and find the value of stress simply there. All right. So let's just find that value. Okay. So I should erase probably some information to get some space. All right, you guys are good for erasing? So what I'm gonna do, I'm gonna erase this guy. I'm gonna erase this guy as well. All right. So let's see. So sigma is equal negative my over I, starting with the top one. I'm gonna say for the top. So negative, the force, the moment is 4 kep, but since we're gonna put everything in inches, I would say already let's just change this one in terms of inch. All right. For the top, y of top is 3.4 inches. The moment of inertia, 91.73 inch to the power of 4. Okay, so the answer to this would be 4 times 12 times 3.4 over 91.73. It would be negative 0.178 KSI. It is less than 0, so it is the maximum compression. So your sigma maximum for compression, it is 1.7 KSI. All right. Let's find the bottom one. Negative my over I. All right, negative. The moment still is 4 kip/foot multiplied by 12 inch per foot. Multiply the y of bottom, 7.1, but it is a negative, don't forget, because it is at the bottom. Your y goes like this, positive. From the neutral axis up is positive, so this is negative. Over moment of inertia, 91.73. All right, so from this, sigma b would be positive. 4 times 12 times 7.1 over 91.73. You got 3.71 KSI more than 0. So it is under tension. So we can say sigma maximum for tension is 3.71 KS. All right. Questions? Okay. So let's continue. All right. So the next thing is the concept of principal stresses. It means that if we have a stress block like this, for example, and a stress block, how much we need to rotate it to reach the principal stresses, meaning the maximum possible normal stresses. And if even that's the case, what would be the values of the principal stresses? All right. So first, talking about just a rotation, pure rotation. If I rotate, so let's just show this. So if I rotate from x-axis would be positive, right? With the angle of theta, the sigma x, which is a new stress on the rotated system here, and sigma y prime, and tau x prime y prime on the new rotated system can be found using these equations, which is, they are in your handbook, by the way. All right. So if this is the case, and these are the formulas for you, right? The question is how we can, so let's just plug in these formulas and find the values corresponding to the rotated stress block. So we have the original system, we rotated, we want to find what would be the values. And you can see these values are related to the stress in the original block. Sigma x, sigma y, and tau xy. All right, so let's look at it. Okay, so on this example, we are asked to determine the normal and shear stresses acting on the inclined plane AB, solve the problem using the stress transformation equations, and show the result on the sectioned element. All right. So this is so you have original block. So let's just look at the original block first. On the original block, you have the sigma x. There is no sigma x, right? There is no normal stress as shown to you in the x direction, so 0. Sigma y, as you can see, it is compressing. It is compressing your member. So it is negative. So we will show the compression negative, 15 KSI. Tau xy is equal to, all right, so tau xy's equation is that it is positive or negative. So determine the shear stress to be positive or negative. So we're gonna do this. You're gonna look at how I told you what does it mean, right? What is the first element? What is the second element to use the shear stress, right? So on this one, right? So we're gonna do this. This is corresponding to plane, as I told you. This is corresponding to the direction, correct? All right. So when I have system like this, okay. When I have a system like this, this is a plane. Let me show you with better color. All right. This is a plane, right? In the x direction. Also, this is a plane in x direction. All right. This plane is positive plane because it is in front. This plane is a negative plane. All right. We can have the same discussion for the vertical elements. For example, you can say, here I have this y plane on top, which is corresponding to positive plane, positive y plane, I would say, and this is x plane, all right? And this one at the bottom here, this one is corresponding to negative y plane, negative x plane here. All right, so this is how you understand the plane. Second item is the direction, rightward positive, upward positive, leftward negative, downward negative. All right, so this one, the direction would be easy. For the direction, you simply would say, all right, this is my positive, positive and positive. The multiplying of these two positiveness and negativeness is going to tell you if your tie is positive or negative. What does it mean? For example, look at this. If I select this side, all right, this side, based on the way that I explained here, it is this side, right? So on the, it is a positive x plane. So this side is positive x plane. You need to multiply this by, you look at the direction of the shear stress. The direction is going to downward. It is negative, right? So it is a negative direction because it goes down. Positive by negative, so your tau is a negative value. That is how you realize where the tau is positive, where it is negative. As soon as, if you do it for one side, it is for the whole block, by the way. You would be good for the whole block. If you're gonna find the same, by the way, you're gonna find the same thing if you go with any other the four faces. It would be the same idea. You're gonna find negative for all of them. You can try it. So it is negative based on this calculation. Positive by negative is going to end up negative. So we're going to put a negative 6K aside here. All right. Having this set, you are set to use these equations to find the rotated value of the stresses on the rotated member. The only thing you want to pay attention is that, all right, so this is, it is asking you to find the AB, right? And our rotation, as I told you, would be positive, goes from the horizontal positive x side, x axis. So you're going to rotate positive counterclockwise if you go from the x axis, all right? So on this member, really what is happening is that you used to have this block, now the block is rotated. So the block is like this. All right. So in a way, we have rotated, right? Positive 60 degrees. All right, we have rotated positive 60 degrees. So your theta of rotation is also 60 degrees. So using this information and this information, let's plug everything in this expression here. So we can even probably work on that. We don't have to rewrite that. So let me write it in this way. So the angle you have found is 60 degrees, right? So this guy is 60 degrees, this guy is 60 degrees. Sigma y is negative 15. Sigma x is 0. All right, this would be your sigma x prime. For this one, again, theta 60 degrees. So you need to multiply it by 2, by the way. Don't forget that the sine of 120 would be there. So theta is 60, not 2 theta. Tau xy, negative 6. By the way, this tau was negative 6 as well. All right. Theta would be 60 degrees. Tau y would be negative 15. Sigma x, sigma y, 0 and negative 15. sigma y, negative 15, sigma x, 0. All right, here, angle 60 degrees, tau negative 6, 60 degrees, sigma x 0, sigma y negative 15. All right. So let's find the values. We would say 0 minus 15 over 2 plus 0 minus 15, right? Would be plus 15. Times cosine of 120 over 2, okay, plus negative 6 times sine of 120. All right, so this one would be negative 16.45 KSI. All right, what about the second one? Negative 15 over 2 minus 0 minus 15 would be plus 15 times cosine of 120 over 2 minus 6 times sine 120 would be 1.45 KSI. And this one would be, so it is negative. So there are like 3 negatives, right? It would be 1, 2, and 3. So it would be positive, right? So it would be 15 over 2 times sine 120 plus minus 6 times cosine 120. So this one would be 9.49 KSI. All right. Okay. So you have found the stresses on the rotated block. So really, what does it mean you have found here? Let me show you. Probably I can erase this one too. All right. So what is going on here is that this is equal to, so you have rotated your system to become something like this, correct? This is your rotated system, right? Now, this is -60 degrees rotation you have, all right? So on the x-axis, you have negative 16, all right? So this is your x direction. Let me do it in this way. All right. So here you have your sigma x prime is equal to negative 16.45. Your sigma prime y is positive 1.45. All right. Your tau is positive, meaning that my positive side, I need to go to the positive direction. So that would be my direction because it is positive value. When you draw one of them, you know that you need to have equilibrium, so you can write the rest of them. Just following the equilibrium. Okay, this would be the rotated shape of your problem. All right, questions? Okay, that's it. Thank you guys for attending here, and I hope that this session have been useful for you, and wish you luck for your exam. Thank you, and have a good rest of your day.
Thanks, Dr. Soltani.
Thank you.